Every single one of them has to be addressed, and you have to look at it and analyze it. And so there's not like one cookie cutter. Every time you see this, here's the answer. I'll give you one last example because I know you don't want to look at this anymore.
Give me a headache.
I know. Sorry.
Wait, if you take like a really small number, like let's just take that 1/10 for example, and you square it, does that get bigger or smaller?
Let's talk about that in a minute.
Okay.
That's why I put that on the board.
Okay.
Okay, look at this expression right here. You see this? Let's just plug in a value of n. If n is 1, let's see what we get. 1 plus 1 over, or sorry, raised to the 1, which is 2. Okay, let's plug in 2. 1 plus a half, what? Second, which is 3 halves squared, which is 9/4. Agreed? And that could keep going all day long, right? So what would happen if n gets really big? N gets really, really big here. Let's see. What would happen right here? What's 1 divided by a really big number going to do?
Really small number?
Let's get really small, right? Really small? So the inside of this is 1 plus a really small number, which should be just a little bit bigger than 1, yes? So I'm just going to write this, see if you agree. That's just a little bit bigger than 1. That in there is a little, just tad bit. As n gets big, that's what happens. But then I'm raising that to what? Nth power, which is huge. Big. So I have a number that's really close to 1 that's being raised to a huge power. We know that 1 raised to any power is what? What's 1 raised to any power? 1. But this is just a little bit bigger than 1. And wildest dreams would think that it's going to be what it is. All right? If you let n get huge, all right? So in this expression, if n goes to infinity, gets huge, 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 grows without bound, this right here, right, it was 2, then it was this, gets closer and closer, it keeps on getting numbers out. The number it goes to is that number. Have you ever heard of that number before? E? E is approximately 2.71. Uh-oh.
Forgot.
Yeah.
Sorry.
Yeah, just someone can do it on the calculator. 2.71. I can't believe I'm having a brain fart right now. 8, I want to think. I want to say that that's what it is. 2.718. I can't believe I...
2.718.
Okay. All right, that's good enough then. All right. Have y'all seen this before? It's called the natural exponential base.
Oh.
It's a number. It's a number. We're going to study it in this class.
Like pi.
It's like pi. It's called irrational.
Yes.
That's what this is. If you can go and get bigger and bigger, this actually gets closer and closer to this number. And that's actually how we define E. E is defined to be this as n goes to infinity. It's weird shit, I'm telling you right now. It's weird. But that's the way it is. You have to analyze. This is going to 1, that's going to big. What happens? You know, does it blow up and get huge? Does it go to 1? What happens? No, they like compromise. They meet in the middle. They say, you know what, we'll just be E. Okay, you want to be E? We'll be E. And that's what they are. And if you change this, crazy. If you change this to 2, it's E squared. And if you change that to 3, it's E cubed. It's weird stuff. So that's, I don't know how I got to that on that function, but yeah, let's get back to the basic functions here.
So side note.
Side note. All right, the next one is the absolute value function. The absolute value function. F of x is the absolute value of x. You seen that before?
Yes.
All that function does is if you plug in a positive number into it, it just leaves it alone, right? But if you plug a negative number into it, it changes it to positive. Right? So the absolute value of 4 is 4. The absolute value of negative 4 is 4. So when you draw this, it creates a V, not a parabola, right? Not a squaring function. It's a nice sharp corner. Now, this absolute value function is the first function that we have in our list here, and it's actually the last one, that we can write as an example of what's called a piecewise function, which we will study a little more later. It's a function that I can define by using two different functions. Watch. So what I'm telling you is I'm going to tell you what f of x is. I'm going to define the function right now. Like if I say f of x is x squared, everyone knows, okay, whatever gets plugged in, it gets squared, right? Here what I'm saying is whatever gets plugged in, here's what you do. If what you plug in is bigger than or equal to 0, right? Then just leave it alone. So if I plug in 4, is 4 bigger than or equal to 0? Yes? Then just let it be 4. On the other hand, if x is a negative number, so give me an example of a negative number. Negative 1. So would negative 1 be less than 0?
Yes.
Yes? So what do you want me to spit out?
X squared.
That won't work for like negative 3. So let's use negative 3 instead. Negative 3 goes in. Is negative 3 less than 0?
Yes.
Yes? What do you want to spit out then? You want positive 3, right? How can you turn a negative into a positive? Times it by a negative? Can't you? Okay, great. Can't use that. You said absolute value? Whoever said that? Okay, that's the function I'm trying to define right now. Okay? Negative x. That's it. That is actually the definition of absolute value. This is what the absolute value function does right here. This is the way it behaves. If you plug in a positive number, it's just going to spit that positive number back at you. If you plug in a negative number, it's going to take the negative number, right? This is a negative number. It's going to multiply it by negative 1, which is going to spit out positive, isn't it? Do you all see how that works?
It's like a little machine.
It's a machine. That's what a function is. It's a machine. But the only thing is, like, this machine has like a bouncer at the door. And it's like, okay, you positive, you go that way. You negative, you go that way. That's what it is, basically.
Can they actually be ever 0?
Well, look at this inequality right here.
Like never actually.
Yes. If x is 0, you check up here. Is x bigger than or equal to 0? Yes? Then just spit out this. But it actually turns out that it would have worked the other way also. Because
The only point that's going to change is 0, which either way comes out 0.
0 and negative 0 are the same thing. Because 0 is neither positive nor negative. And both at the same time.
Are like a real thing?
Yeah.
Oh, wait, 0.
No. There is no negative 0. 0 is not a positive or a negative number.
0 can be considered either, so it can be considered negative technically.
It depends on how we want to define what positive is. All right? Yeah, come on. We can get really... I mean, we can. This is...
That's interesting.
Now, when it comes to even and odd numbers, right, 0 is an even number.
Yeah.
Okay, but it's not positive, it's not negative. All right. Okay, so this is called a piecewise function because it has different pieces, doesn't it? Different paths that you go down depending on this.
I remember seeing that. I just don't remember ever actually hearing a term before.
Yeah.
Piecewise?
Yeah.
Okay. Now, this is the way all books write it, but I kind of wish it was written the other way. Like if x was less than 0, then, you know, something like negative x. So it's kind of like you go through and you say, okay, first you check, here's the output. This is the other way around. It's like, okay, here's the output, but that's the condition for it to be that output. So to me, it just seems better the other way. But I don't get to choose the way things are done. So just like that. Sometimes you won't see if, sometimes you'll just see a comma. And it's understood that that means the same thing. All right. Those are your functions. Those are your library. That's your library of functions. Everyone should know, absolute value of x. Boom. Everyone knows what that looks like. Now, quickly here, if I ask you to graph this function real fast, everyone knows what that looked like?
Yeah.
Okay. That's your identity, right? Any idea what this function would look like? I'll call it g. Any idea what this would be? It would go down left to right? So it would go like this? Everyone agree with that? Yeah, good? Yeah. Okay, go back to that absolute value for a second. We just defined the absolute value function. Oh, shit, I'm in the wrong class. It's an integral sign. Okay. X if x is greater than or equal to 0, and negative x if x is less than 0, right? So if I'm bigger than or equal to 0, I want to draw this. So if I'm from here over, I want to be the blue one, right? And if I'm to the left of 0, I want to be the black one. That's your absolute value function.
It's kind of like
You see it?
railroad tracks and trains.
Yeah. You're switching. It's like I'm going to be this function first, then I'm going to switch to this function. Do you see that? So you don't want to just look at the v. It's like, yeah, it's a v. Like absolute value, it's cute. It's a v. Like, no, it's two functions put together.
So, that kind of, because I've seen in the book there's like equations that have absolute values that kind of like makes sense.
Yeah.
Well, like, what about the ones where, like I'm looking at the book too, like there are ones where like there are two functions, yes, and then there's a random third variable somewhere in the middle or something like that.
Yeah. Which one are you looking at? Anything particular?
For example, 35 from the homework, I suppose. That's one example.
Yeah. Okay. So that's why I'm going to get to this next note, which is we're going to talk about one special function, and then we're going to talk about your question, which is graphing a piecewise function. Okay. So this is one of those functions. Where are my computer science majors? Any computer science majors? Yes? This is a function that's used in computer science quite a bit. In computer programming. All right? The greatest integer function. Sometimes you'll hear it or see it written int x. Int x. But the standard notation most people use for it is a bracket, set of brackets around x. And let's read the definition of this function, because it's a sentence is what describes this function. Okay, this is equal to the greatest integer, yep, less than or equal to x, not 0. I don't know if you said it 0.
What's it? X.
Mm-hmm. I've also seen, I believe, in some books a double bracket, but the greatest integer less than or equal to x. So
That bracket,
that's what this means. So you know how the absolute value, we kind of know what that means? When you see the bracket, you need to know it's referring to this function. Okay, so it's let's get an idea of what this is doing. So let's try and graph this. And to do it, I'm going to make a t-table, x, and then here's the greatest integer function. Let's plug in 0. Okay, 0 goes in. I would like for you to tell me the greatest integer that is less than or equal to this number. Well, what's an integer? Do we know what the integers are?
The whole number, so it's not like a fraction or a decimal.
Okay, so the integers are the numbers 0, 1, 2, 3, 4, forever, right? All your counting numbers.
They're whole numbers?
All your whole numbers, and backwards the other way, -1, -2, forever that direction. These are integers. All right? What was that? Negative. Okay. So maybe what I'll do is, here's where we're going to graph it, right? Here's where I'm going to think about this. I'm trying to plug 0 in, right? I'm trying to plug this number in. I'm going to draw a number line here. 1, here's -1, here's -2, here's 2. So I'm trying to plug 0 in. What is the greatest integer? Greatest means greater is to the right, less is to the left. What is the greatest integer that is less than or equal to this? Well, 0 is an integer, so it's equal to itself. So the answer should be 0. I'm going to do that in a minute, yes. If I plug in 1, what happens? 1. Plug in 2. 2. If I plug in any integer, it spits that integer out, right? This looks like the identity, doesn't it? Kind of. So if I plot, I got 0, 0, 1, 1, 2, 2, right? And I can keep going. But if I connect that with the straight line, I just screwed up. So let's look at some numbers in between. So how about we go with a number something in here, like 0.5, 1/2. How do you want to do it? Half, 0.5. So let's go over here to 0.5 on this number line, which is right here. And I want you to tell me the greatest integer that is less than or equal to this. 1 is greater than it. It says greater. So it's the greatest integer you can find that is less than or equal to this. So 0, right? It's going to spit out 0. Is 0 the biggest integer I can find that's less than that? Yes? Okay, so if I plug in 1/2, it spits out 0. What if I plug in 3/4? 0 again. What if I plug in 1/4? 0 again. In fact, anything in there will be 0, won't it? So it'll be solid here. But what happens when I get to 1? It jumps up. So I need to put an open circle here like this. Do you see that?
So that's why it has those the open dots on it.
Yeah, when I show you the whole picture, if you're looking at it there. Now, what if I try something in here like 1.5? The greatest integer less than or equal to that is 1. So at 1.5, you're up here at 1. If you're at 1.2, you're at 1. Understand this? And that'll be the same until I get to where? 2, and then it jumps up. And then I keep going. It'll do that again, and then keep going like this. And if I go backwards, it does the same thing in the back reverse direction. They call this a step function. I wonder why.
Well, you did say jump.
Hmm?
You did say jump.
Yeah.
The X. Yeah.
So this is an example of what we call a step function because of the way it looks. But in computer science, they call it the floor function. And the reason is because what happens is you look at a number, right? You take a number like 3.7521. And what you decide is because of memory, because of increasing the speed of your program, whatever it is, you decide that you don't need all the stuff after the decimal point. You just need the 3. Maybe that's what you need for your application. So you decide what you're going to do is cut this stuff off, regardless of what it is. Even if it was 3.0023, it's not the same as rounding. Rounding, remember rounding in grade school is like round up, round out. This is not what this is. All this does is it takes the number, like what would the greatest integer function at this be? 3. Here? 3. Do you see why they call it floor? Yeah. It's like levels, right? You're at the third, 3-story building, 3.75. You're dropping to the next the floor right below you. You're cutting off this junk, dropping to the floor.
So you're just going to whatever integer
is below you.
Is below.
Yes. Okay. Now you can also have a function in computer science called ceiling, which has a different notation. We're not going to talk about it, but it's the reverse. What it does is it takes the number and it would go up to the next integer. So like,
yeah, just like instead of complete dots, it's open circles. And
it would be this.
That's it's gonna start.
It just moves it up. Because what you do is, if you have 0.5 instead of being 0, you're now 1. That's all. If you're 1.3 instead of being 1, you're going to be at 2. So it just goes up for everything. Sometimes they use the ceiling, sometimes they use the floor. It just depends on what they need in the program. But it's a common function used in computer science. All right? How am I doing here? Pardon? Got it. Okay. All right. So now let's talk about piecewise functions. That'll help you with your homework. And you were referring to number 35, yeah? Why don't I just look at 35? Okay. The instructions here, there are a lot. There are a lot of instructions. Let me just get the function up here. See, this is a great example of a problem that I may not have really shown you before we left today, that I would expect that you could kind of extract the information from today's discussions and formulate your own idea of what to do. It's asking you for a lot. Find the domain, based on the graph, find the range, locate any intercepts. Is the function continuous? Graph it. I'm going to start with a graph, all right? I'm going to start with a graph. This is like that bouncer at the door, right? Coming in. I've never used that. That kind of seems like that might work. Y'all get the idea? It's kind of cheesy, but you're going to plug X in. The first thing you have to do is determine which way you're going to go, right? Door number 1, 2, or 3. And that's going to depend on what you plug in, right? If what you plug in is bigger than or equal to -2 and less than 1, you're going to do this. If your X value that you're plugging in is 1, then 5. And if X is bigger than 1, you're this. So do you see there's only one number that's ever going to go to this one, right? This is like that one VIP section right here. All right, I'm going to try and draw this. I'm going to first take a look at the different pieces, which is where we funnel people, funnel the inputs coming in. I have one that's between, when my x's are between -2 and 1. Now graphically, here's -1, here's -2, here's +1. And I just want you to imagine that what I've done is I've created like a section of the plane over here, right? Just this section. Everything here, right, has to do, or not, I shouldn't say everything. It's just between these, right? Everything in here between -2 and 1. That is this, right? That picture? Agreed? Then, when I'm actually at 1, what am I? 5, which there's only one thing, right? At 1, I'm at 5. 1, 2, 3, 4, 5. So when you go to 1, here it is, solid dot. That red dot is the first point that I put from my function. Everyone agree that that's there? Any questions on that? And then I have another region, which is when x is bigger than 1, which is this way, isn't it? Which I will try and draw now. If I have green, I do. And that's going to be, what, this direction forever? So I can't put another line over here, so I'm just going to put a little arrow. Everything over here is green. That's this one. And I'm also going to just kind of cross that out. Why am I crossing that out? It's not important because our domain has nothing to do with that, right? This function only goes from what? -2 to 1, through 1, and then past 1 forever. Yeah? So could you answer the question right now of what the domain is? What is the domain? -2 to infinity, forever. Right? This graph should go from -2 all the way over. Now at 1 I have a little hiccup. At 1 something happens. It's kind of weird, but it keeps going. What's that?
So you wouldn't do that. You wouldn't do -2, then 1, parentheses u, and then.
No.
Includes all the points included.
No, because at 1 I'm actually defined. Like I'm defined at 1, right? This may have been a little premature. All right, maybe when we draw the graph you'll see it. But do you agree we could start at least thinking domain now?
Yeah.
Yes? Okay. Okay. So we'll leave this as an open question. Maybe that's not right. It is, but let's see why. Let's see why. Okay, so let's start with this blue section right here. What I need to do is I need to graph this right here. Okay, does everyone know what x looks by itself? What does +3 do? Raises it up 3, right? So we all know that this is the identity. Now I want to be very careful about drawing as precisely as possible because, you know, this is 1 unit, this is 2 units, this is 3, this is 4, this is 5. It's better if I had graph paper, but I'll do my best. So here's my slope, right? That's x, and then move it up 3. So that's going to be 1, 2, 3. So it's going to go from this point up 1 over 1, and then down 1 over 1, and then down 1 over 1 again. I think I'm going to be like this. That's not very good. Okay, like that. Do y'all kind of agree with that?
Yeah.
I'm having a little trouble figuring out what's happening over here. Can you plug -2 into the function for me? Plug in -2. Is that allowed? No. So try and send -2 through the bouncer here. -2 comes. Okay. Is -2 bigger than or equal to -2? Yes. So come here, plug in -2, and what would you get? That looks like division. -2 plus 3, which would be 1. So this is 1 unit high. So I actually have a solid point right there, don't I? It's solid because I'm allowed to be -2.
That's just going to look at you funny, but it'll let you in.
Yes. Then you plug in 1, right? What happens when you plug in 1? Well, not here, right? You have to be here. Right? Do you agree?
Oh,
You can't be here because this is less than 1.
so this is fine.
So we know that already, right? But we kind of knew that. The question is what's happening here, though, right? Well, let's not plug in 1 because we can't, right? Why don't we try and plug in a number that's kind of close to 1? Like, closer.
0.25?
That's closer to 0.
1.7.
That's on the other side.
0.75.
Okay, 0.9, right? So what I'm trying to do is figure out what's happening here. So why don't we plug in like 0.9? What would happen? So which one are we in? 0.9. We're in the first one, right? 0.9's in here. What's 0.9 plus 3? 3.9. Okay, try something even closer. 0.99? 3.99, right? 0.999? 3.999. So what's happening is I get closer to 1 here on the black function. It's getting closer to 4, right? This is 4? It's getting closer to 4, but is it ever getting there? No. Okay, there's my little open circle. You see it? Now we've got the function drawn from -2 all the way nice through to 1. I realize at 1 I have a little jump, right? A little break in my graph. And then what we need to figure out is what's happening to the right of this. So to the right of it, I'm supposed to look like that, right? This is a -x, which is the identity pitched downwards instead of upwards, right? And then moved up 2. So I'm looking at this, moved up 2. 1, 2. Do you agree with that? But I'm only supposed to draw it where? Past 1. So that means over here. Do y'all see it? If this continued through, which it doesn't, if it continued through, then that would be, you know, this through the y-intercept. But because of the restriction on the domain, I'm only allowed to draw it past 1. Is this point getting closer to something? Like if I try and plug in a point here that's a little bit on the other side of this, what would be a number on the other side of this?
1.01.
1.01? Which of these would it go into? 1.01. The last one. What's negative 1.01 plus 2?
1.01.
What is it?
1.01.
1.01? No. I'm saying you're plugging in negative 1.
0.99.
Let's do this one. 1.1 plus 2. Let's say we're picking 1.1, which is right here, right?
0.9.
Plug that in. It'd be 0.9. But if you go negative 1.01 plus 2, it'd be 0.99, right? And so it's getting closer and closer to 1, which is right there, but it never reaches it. And now if you take all that crap out of there that we put in there to help us draw, may I take it all out now? That is the graph of that piecewise function. So you need to be able to do that. Graph paper might make it easier. If you're ever hesitant, like what's happening over here, just pick a couple of points that are bigger than 1 and just plot them. You always can do that, but we're most interested in, like, can you do this as fast as possible, you know, without having to just keep testing points. There were a couple of other questions in here. Was this function, or were there any X-intercepts? Yes. This right here hits, right? Somewhere. Where? Well, that's the third function, right? Where's this 0? At x is 2, right? So you have an X-intercept at 2. Is that a question, sir, Ryan?
No, never mind.
Okay. So we would have an X-intercept. How about a Y-intercept? Do we have a Y-intercept? Yes. 3. Right? Find the range. Ooh, this range is interesting. Oh, wait, was domain? We skipped over domain. Are we okay with this domain?
Yeah.
It's still good?
Yeah.
Negative 2, I go to 1, but at 1 I'm defined. Right? So if that wasn't there, I would have to use a union. Right? If this point wasn't there, I'd have to use a union because I would have nothing happening at 1. But since it's there, I can just follow through. Range?
Negative infinity to 4, parenthesis, union, and I'm not 100% sure how you do it.
Okay, so this arrow means it goes down forever, right? So we have negative numbers coming up. I'm getting all the negative numbers, and then I come up negative. How about right there?
Yes.
I do get 1, right, out this side? So I've got all the way, no problems yet until I get to 4. And at 4, that's where the graph stops, with the exception of one value, right? So I know it's from negative infinity up to 4, not including 4. Good.
Then
Unioned
then just 5.
with just 5. How do I say just 5? Just the number 5.
5 bracket.
The brace. The singleton. The singleton. Remember the singleton notation? So it's all the values between negative infinity up to positive 4, not including 4. And then the only other thing that comes out is 5, the number 5. And that happens, right? That happens right there. So we've got domain, got range. Is the function continuous? So we haven't talked a lot at all about continuity and continuous. In this class and in the beginning stages of Calculus 1, you will hear this word, continuity. Continuity just means, can you draw your function without picking up your pencil? If you can, it is continuous. If you cannot, it is not continuous. So let's start at the beginning. Can I draw this whole thing without picking up my pencil? No, because at this point, I must pick up my pencil, draw that point, and then come down here and go here. This is not continuous. We have a problem happening where? At 1. So what we would say is that there is a discontinuity at 1. Because if that wasn't there, then we might be able to do it, right? If you take this, which is which function? Square root function. Is this continuous?
Yes.
Yes. Pick it, go like that. In fact, every one of your toolbox functions, they weren't library functions, every one of those was continuous, wasn't it? Oh wait, hold on. Except for the 1 over x, the reciprocal one, right? The one that we did that was this. You couldn't draw that without picking up your pencil, right? It's not continuous everywhere. There is a point where we have a discontinuity. All right, well, I hope that that's enough to get you going on your homework. We have 2 or 3 minutes. I just want to address this square number, it gets bigger. Yes or no? And that's what you would think, right? Common thought, the square number gets bigger.
Well, apparently it gets closer to
With the
2.18.
with the exception of whenever it's between 0 and 1,
What happens there?
then it gets smaller.
Okay, so if I take 4 and I square it, obviously that becomes 16, so it got bigger, right?
Yeah.
But if I take 1/4 and I square it, that's 1/16. And that's smaller than 1/4. And so what we have is that if the absolute value of x is less than 1, then x squared is less than the absolute value of x. In other words, if you take a number on the number line that's somewhere in here, okay, if you take some number that's in there and you square it, it's going to be smaller than the number that you started with. Guaranteed. But if you go outside of 1 or including 1, then it does work. Then squaring it makes it bigger. So, of course, if you square 1, you get itself, right? So, but if you take a number, anything bigger than 1, 1.1, 1.2, square it, it gets bigger. And the reason why I like to point that out is because if you're asked to graph these two functions together, the first one looks like it's the squaring function, right? So it looks like parabola. How about raising it to the 4th power? Should look very similar, shouldn't it?
Yes.
Okay, so let's just briefly draw it. They both have 0, 0. They both have 1, 1. They both have -1, 1, right? They both have those? And if I graph x squared, I know I'm going to get, something like this. Let's just say this one is x squared. My question to you is, where is x to the 4th in relationship to this?
It's a little bit narrower, I suppose.
Okay, so let me take an example, number 2. 2 squared is what? 4. 2 to the 4th power, though, 16. So the blue one should be way on top of the other one, right?
So then,
So this, from this point, this blue one's going to be above this one, right? But the other way around is that if I take a number like 1/2, I square 1/2, I get 1/4, don't I? But if I take 1/2 and I raise it to the 4th power, I get 1/8, which is smaller than 1/4. So from here to here, the blue is below. And then over here it goes like that, and then it goes above it. Do you see the difference? All right. That's it. Are we done for the week? We are done for the week. Signed. Everyone's signed in. I have not. Still have people's work, but I think these are people who are no longer here. So this is that assessment test. If you want it, you can have it. If not, you'll have a good weekend. Do your homework.